Good morning, everyone. Thanks for joining us this morning. Just before we get started, a quick reminder on the code of conduct and all the different points of contact in case there is something you want to bring to the attention of them. And yeah, we thank you for being here today. We hope Ilana Urbach, who's online, who will be monitoring the different questions and come up on Zoom and on the Slack channel. You can find in the Slack channel a link to where all the slides are found for the different presenters. So I encourage you to check that out. They should all be uploaded at this point. And we hope we'll find this session interesting. There's been a lot of questions coming up, at least the first day and later on as well, on image quality. I think we'll address some of those topics that may be of interest. And because we figured we wouldn't be able to cover or anticipate all the questions you may have, we will also have a 15-minute Q&A session at the end where many of the people who've worked with the system who are all here today, not all of us will be presenting, but we're all here. So for the most part, so we'll all be able to help answer some of those questions you may have. And without further ado, we'll begin with Keith Vechtel, who will be giving a summary on the image quality of the Rubin Observatory, but I don't know how do we do it. Thank you.
Thank you. Okay, so I'll give an overview on the image quality. And my goal was to try to make it accessible for everybody. So I think for folks on Rubin Observatory will be familiar with some of these details. But I'll try to walk through and explain what some of the metrics mean, how to interpret some of the results, and more in details that you'll see later in the session. So just the very fast one slide summary of the current status. So Rubin Observatory can already deliver an arcsecond sky survey, right? That's a major achievement from the past year. The current estimated instrument contribution to the PSF full width half max is at the level of 0.45 arcseconds. So when we say instrument, this includes the optics, the camera. It does not include the dome seeing, and it includes the atmosphere. Okay. The pre-LSST data are consistent with the expected distribution of the free atmosphere median seeing at Cerro Pachon, so at the level of around 0.7 to 0.75 arcseconds, and a median dome contribution of around 0.3 to 0.4. For reasons that we'll discuss, these are actually fairly challenging to exactly disambiguate, but these are our current estimates. The majority of the PSFs are well described by their second moments. I'll show some evidence of that later. And then part of the reason why we felt confident starting the survey now, a significant part of that argument, is that we believe that we can continue to make progress in parallel with standard LSST survey observations over the next year. There are some targeted on-sky engineering tests that we'll need to do, but during the early operations period, we were able to validate that data collection analysis approaches, and so we're confident that we're going to be able to continue making progress. We're still not meeting all of the design specifications consistently, but as you'll see, we're quite close to making progress. What you'll see today, you can find more details in these two tech notes, the early operations on-sky performance and the image quality improvement plan. These were part of the technical documentation package that we used for the start of LSST, but we made them as tech notes so that the whole science community could read them and see for yourself. Also, Brian Stalder gave a summary with more discussion at the Monday SAC parallel session. Okay, so this is the current image quality budget as it was known in June 2026. So basically, it's trying to break down the various contributions. So you see there's a part from the static optics, which you can think about as including the AOS and the mirror thermal gradient, something that actually affects the mirror figure and is steady throughout the exposure. There's various dynamical optical components, and these have to do with vibrations or movement of the mount, for example. There are the various seeing contributions, including the atmosphere and the dome seeing. And then finally, there's the instrument contribution, which is primarily the diffusion of photoelectrons. And so we've been able to provide estimates in all these different areas. This is the distribution of the PSF full width half max. This is going from April up through mid-July before the storm. So this is the period once we had achieved kind of stable performance that we were happy with to start the survey. So on the left is the PDF, and on the right is the cumulative distribution. So this is where we can basically see that, in most of the bands, we're at the level of about an arc second. It's a little bit more challenging in the bluer bands, as expected. But this is where the statement that we can already deliver an arc second sky survey comes from. So next, I want to talk about how we estimate the instrument contributions to the PSF full width half max. There's basically three different approaches that we use. None of them are perfect, right? They all have limitations, but we see that they're highly correlated. And the ensemble of measurements, I think, gives a realistic picture of where we stand. So the first of these is the variation across the field of view. This is basically attributing the difference between basically the 5th percentile and the 95th percentile of the PSF full width half max across the field of view, basically looking at each of the sensors. If you basically attribute that variation to an optical contribution. A second is if you take what we call an optics plus camera diffusion. This is looking at the measurements from the corner wavefront sensors, plus accounting for the charge diffusion within the camera added in quadrature. And then finally, we have an estimate, the delivered minus the estimated atmosphere. For the estimated atmosphere, we're using a quantity that we call the donut blur as a proxy. And then we subtract off the diffusion from the photoelectron. So it's three different methods. Just to provide a little bit more detail on the donut blur, because you'll probably see more discussion on this later in the session today. You can think about the donut blur. It's basically a convolution kernel that's applied during the fitting of the optical wavefront, where if you take these measurements from the corner wavefront sensors, you basically we find that in order to get a good fit, you need to apply this convolution, and that convolution is basically accounting for effects of the charge diffusion, the atmosphere, the dome seeing. So it's difficult to distinguish all of these different components, but we find that in most cases, it appears that the variations are most correlated with the atmosphere, and that's a dominant contribution. The two images here show examples of what these basically donut images of the pupil look like in a case where we have a smaller donut blur on the left and then a larger donut blur on the right. So that's functionally how we measure this. Okay, so this is a summary plot that you may have seen before that basically shows how all these quantities evolved throughout the early operations period. So again, you can see that these different measurements in the blue, the purple, and the red, the different ways of estimating, they are correlated with each other from night to night, and we see that they vary even within the night. But there are some differences that are just captured by these different approaches. And just for comparison, the orange here is the ellipticity contribution. And what's interesting is that's been relatively stable throughout this early operations period. But the fact that it's stable as we've been improving the PSF full width half max is actually showing that we're achieving a better control of the optics contribution. This is the distribution of what the ellipticity looks like. These are per sensor values, okay? And so what we see is that there's often some variation in the ellipticity from visit to visit, but also within the individual visits across the field of view. For almost all of these quantities, we get measurements for each of the 189 sensors. And so it's a huge amount of data that we have to kind of compress and summarize, to make sense of what the performance is. For the ellipticity in particular, the design specification is that the median should be within this green shaded region. So this is an example of where we have substantial overlap with our design specifications, but our median value isn't quite where we want it to be. This yellow shaded region is where we'd like the tail of the distribution to be within. And so there's still, we believe, opportunity to improve the consistency of the ellipticity. One of the new metrics that was developed in recent months is basically it's two different ways of estimating the non-Gaussian and non-atmosphere contribution to the PSFs, basically sort of irregularly shaped PSFs. And so we have two different ways of doing this: a moment score and a shapelet score. The moment score is computed from a combination of third and fourth order moments. The shapelet score is very similar, but it's using a shapelet decomposition, and particularly computing the power that's in these non-Gaussian and non-atmosphere contributions. In practice, what's shown here on the plot in the upper right is that these two quantities are very highly correlated with each other. So they're effectively interchangeable in terms of which you use. But these have been very useful for diagnosing any issues with the PSF. In the future, these could be used to identify the PSFs that are best suited for going into co-addition, for example, in the data releases. This is an example. In the next couple of slides, we'll basically show what these different scores look like in different categories. So these are our best PSFs in the so-called excellent category with the lowest moment and shapelet scores. These are ones that are good. Here's a gallery of ones that are marginal. Here you start seeing more non-Gaussian features. And then these are the ones that are poor. And here, these are really the situation that we want to avoid. We don't want these going into our coads. If you look at the distribution of these scores, this is on a log scale on the vertical axis, important note. And that's good because where you see the tail of this distribution is at the level of like 1 in 1,000, out in this really poor category. And then it's sort of at the percent level for the marginal. So you can basically see that well over 90% of the individual detector images are fairly well behaved and are well described by their second moments. This is what those distributions look like over time. So basically in all these time series plots, what you're seeing is the 10th, 50th, and 90th percentile. And because we were really interested in the tails of the distribution on this one, we also show in this thin gray what the 99th percentile looks like. And so you can see, throughout this period from mid-April on, that the vast majority of the PSFs are in this excellent and good category, and that's stable from night to night. There's other metrics that are being developed. We're going to hear a talk about the guider-based tomographic separation of the different contributions to the image quality by Jackie later the session. So just to highlight that, I think that's a really exciting opportunity that's being pursued now. We'll hear more about that later. And then finally, I think throughout this session, it's really helpful to hear from the community your ideas on, is there additional information, metrics, visualizations that will be useful to help that we should consider developing, or ways of presenting the information to help understand impacts on your science cases. I just want to conclude. This is another one of the graphics that's from this image quality improvement plan. The details of this is what we're going to discuss throughout this session. But basically, we do have a plan, but there's many steps involved. It's not any one contribution that's dominating. It's really getting into the details of understanding all the different components of the system, and it's going to take time. It's going to take months. It may take the next year. And so it's really going to be this very coordinated effort across the observatory. And so I think it's there are challenges ahead, but hopefully you've seen that we've also made enormous progress, and we're confident that we can continue doing that. I'll stop here if there's any questions.
Thank you very much. Can you go back to the graph that showed the distribution of ellipticity, that histogram?
This one.
That one, exactly that one. So it does look like there is quite a tail there of really very high ellipticity, and that probably doesn't correlate very well. Well, let me ask as a question: is that correlated well with these scores that gave good, bad, and indifferent that you were just describing before? And really, what's driving the very high ellipticity nights there?
So when we could basically see that there was issues both by visual inspection of the PSFs and also by this tail of the distribution. And so that's partly what motivated, for example, like Jelko, TQ, and others, Jim Bosch, Lauren MacArthur, to start developing these other ways of characterizing data. What we have found through basically careful studies of these moment scores and shapelet scores is that they really are giving us distinct information that goes beyond the second moments. So this is really like distinct like separate information. For the ellipticity contribution, I think we'll probably hear more from that from Sandrine in just a moment. But what we see is that some of these tails in the distribution, it's kind of like on the periphery of the field of view most of the time. It's basically the challenge of maintaining this excellent image quality across such a large field of view, and that's where our attention is going to be going forward. Yeah. Yeah.
There's a certain amount of coma and trefoil that's designed in. So is the is what you're seeing there in the score the total coma and trefoil, or only that part of the coma and trefoil which is or not designed in?
I'm actually going to recommend handing.
Yeah.
You go ahead.
So the design on this scale, the design would be 0 or close to 0. So all of this is extra.
Okay.
Okay. And I think you can see that the sort of large values, largely correlate to the two worst cases that Keith showed. So this is a different effect that's going on here. The
Thank you.
design has relatively little coma or trefoil.
Thank you.
And maybe I can add a little to Michael's question. I think the moment or shapelet score and the ellipticity are probably not that correlated. They're seeing two different things. This was designed to pick up bimodal or trimodal PSF, so really more pathological shapes that we've sort of seen off and on, not consistently, but occasionally. The variation in ellipticity is the sources that are an area of ongoing active investigation.
Mhm.
So we could say more in the Q&A period, maybe.
Last question.
Thanks. So, since you mentioned that some of the distribution and opticity is within an image, so spatially dependent, how much of the distribution is that spatial dependence within a single image versus over the distribution of images, where most of the images has an elliptical PSF?
Yeah, so you can kind of, so this is a way of visualizing that information. So this is showing per visit quantities, by each night. And so you can see that, again, it's the 10th, 50th, and 90th percentiles of the distribution. So it's basically more common that there's some range of variation within the individual visits, right? Like oftentimes there are, significant portions of the focal plane that are very well behaved, and then it's sort of just along the periphery that you see this tail of the distribution, and so that's part of where the continued attention is going.
Okay. Yeah.
Right. Thank you, Keith. We'll get ready now for some Green Thomas talk, actually. While we do that, let me mention something that I did not mention before, which is that we do expect to go 15 minutes over time. I hope you will all be okay with that. Yes.
Thank you. So the reason, I'm going to give a really, really quick update on the active optics system. This one, the latest one. All right. And because we don't have a lot of time, the way I actually organize the slides is really to give you a summary of the updates without going into a lot of the details. We added a few slides at the end of that presentation for either questions or for consumption afterwards. So that's kind of what I did. But really, I don't know how many people have been here in the past or are new this year to the Rubin Observatory. But one thing I just wanted to go very quickly on what it is. So we do have an active optics system to, in real time, adjust the shape and the position of the optics in order to get the image quality that we need over the full 3.5-degree field of view. And to do that, we have an open loop model, which comes from mostly design, and we have done some tests on Sky to optimize it, and we're still doing that. But that is to compensate mostly the gravity. And then we have a real-time closed loop component, which uses the sensors on the corner of the wavefront of the focal plane. So you see with those blue arrows, and those are actually used at the same time as your image to calculate what wavefront aberration you have in your system, and in real time, meaning every 37 or so seconds, adjust the position of the optics and the shapes of the mirror in order to get a good image quality. So this is kind of the loop that we have. We do have a control loop, and I wanted to mention that because there is some work that we are doing right now on how to optimize also the way we go from those images on the corner of the focal plane to how we actually use that to adjust the position and the shape of the mirrors. So that's kind of the crash course of what the active optics does. And I want to go back to this slide that Keith has shown earlier. And in particular, I wanted us to focus on this little jump down. It's not really a jump, it's an improvement of image quality. And a lot of the work that we've been doing in the last year was really to bring both the average of the average of that PSF and the size of those error bars down, right? Because we need to make sure that both we have a median PSF shape and also a spread over the field of view small enough to do the science that we want to do. So you can see on those images that Keith mentioned, the distribution across the field of view is the blue. And again, apologies for the colors. These are these, and you see that it's actually can spread over 0.2 arc seconds. So that's really what we really worked on in the last year. And that drop was very a final measurement and a first tweak of what we call the target residual. So we did realize, and we kind of knew ahead of time, but we actually spent a lot of time measuring as you close the loop, as you're measuring your wavefront error and you're driving the system to correcting for those wavefront error, we were actually going back to the same place, right? So we actually were the system was doing what we wanted the system to do. It's just that it was not the right place for a good image quality. So that's really something that drove that improvement. And also in that control loop, you have matrices that you need to normalize, and the normalization was not fully correct. So we were limiting ourselves. So that's really what actually drove that improvement. So that's what I mean by I'm going to give you a summary of the areas that we're actually working on. And please, if you need more details, you can go to the slides, and then you can ask anyone who works on the active optic system questions. The first area of research that we're really actively working on, mostly Aaron in a room, so ask all the questions to Aaron, is what we call the measure intrinsic wavefront. So in parallel to those target residual, we really need to make sure that that system does converge to the right points. And we also need to make sure that we put the right shapes on those mirror to begin with. And so there was a lot of study using the actual focal plane as a wavefront sensor to estimate what was that spot that we were always getting to when we were closing the loop with a wavefront sensor. So a lot of work, a lot of really tedious work has been done because, of course, all the measurements have a lot of noise. So the status of this is that we actually have deployed a version on the summit, and we need to, before we go back on Sky, whenever we go back on Sky, we need to fix a few bugs and then optimize it in the next, I don't know, few months after that. The open loop model, I mentioned it earlier. We have it from finite element models. We know it's not perfect. We have tested the open loop model in the lab, both for the primary, tertiary mirror and the secondary mirror, but with only limited gravity vectors. And so we know that when you want to observe a deep drilling fit at 20-degree elevation, it's really, really difficult because our open loop model is not robust at that place. And so we've been in parallel of doing all those tests, doing what we call bounce tests, where we actually take measurement at two different elevation and different rotation, and then optimize and that open loop model. So then eventually we'll be able to go to 20 degrees and have a good PSF out of the right away without closing the loop. Leaky integrator, so that is a work by Craig Lage, and it is to make sure that any other perturbation in a system is taken into account as we are closing that loop. So for instance, we know we have some temperature drifts. We know we have environmental differences from one image to the other. And remember, we are closing the loop, but we are not closing the loop on the same part of the sky. The main and the strength of the Rubin Observatory is to move from one field to the other, and the active optics system needs to adjust as that telescope is moving around. And that's the challenge. It's really to keep that everything in the right alignment. So everything needs to move, but everything needs to be giving that fixed position on the image. And so that's what this very straightforward control loop is being studied and adapted to the AO system. Lots of work has been also on the cleaning up of the donuts that we're using in our for our study. So you see, we need to take into account donuts from each of those CCDs that are defocused. And then sometimes they're very blended. Sometimes they're noisy. So we need to make sure that a lot of cleanup is being done ahead of time of the reduction. So that's another work that is being done actively right now. We also have to make sure we optimize our pupil because our wavefront sensor does depend on how well we know that pupil and how well we define what those donuts should look like. We also have to make sure we do the right image, take the right image signature removal. So we realized at some point that we had hot pixels that were actually giving us a lot of noise in our measurements. So that is being actively also worked on. So how to do even better improvement of the measurement. One thing that is really interesting is that we have tested some artificial intelligence algorithm, and that gave really, really good results. We tested TOTS, for instance. Peter Ma, I think, has a presentation on that. Okay. So there's more slides in the back of this presentation. And granted, it was a really good night, but we're very excited about using those. Timing, we need to make sure, as I mentioned, we actually measure in one position and correct in a couple at n+2. And so we have to make sure that we are actually correcting at n+2 and not n+5. And so we're really, really attentive to that, what we call the visit gap, and also how quickly we can measure and apply the correction. And then giant donuts, so we're defocusing even more the telescope to understand some of those pupil variation that we're seeing. I re-emphasize the AOS improvement plan. There's a lot of material in there. If you want to know more details, you can look at the slides and you can look at this tech note. And I'm going to stop here because Keith already showed the ellipticity. So just all that work will also improve the ellipticity, because one thing that I want to sensitize everyone to is that even when you just defocus this telescope, you do get ellipticity on the size of your focal plane. And so any work that we do to realign the telescope will help with ellipticity.
While Brian sets up the presentation, let's have a quick one question if there's any. And if not, we can wait until the Q&A. Yeah, Tony.
I just wanted to emphasize something that Sandrine said, and that on the plot on the right, it's possible to have just horrible, huge, fuzzy PSFs and have extremely low ellipticity, and you don't want that. For dark energy, you want very good PSFs and low ellipticity.
Thank you.
Okay, I'm going to talk about some of the engineering efforts that we've made progress on over the last year. I think I can convince you that we made a lot of improvements, and I think it shows in how the AOS is really coming along in its performance. So I'm going to review exactly what this environmental awareness system is about. The dome thermal control, describing our techniques and strategy in managing the environment around the telescope. Then the mirror system as well, how we create a stable environment for that to allow the AOS to function as designed. And then give a quick summary on where we sit right now. So the Environmental Awareness System, or EAS, basically is the coordinator of all the thermal systems and sensors around the observatory. It feeds that information into all the other components and subsystems, and then actually creates a logical control and coordination between those subsystems. And we've split the logic and control into two basic modes: daytime, which is preparing the observatory for the evening observations, and then nighttime control, which is to stabilize the system consistently during the night. Starting with the dome, we have the HVAC system, which we're constantly tuning up to get better performance during the day to condition the dome. And over the last year, we went from 0 working louvers to 6 louvers in November, and then 12 total in April timeframe of this year. So substantial progress, and I have some plots later on in this deck to show exactly, how much better it is. Daytime performance. So this is over, I think, several months, 38 nights. So a couple months of data on the left here that shows our preparation for the evening conditions. So during the day, it gets warmer than inside the dome. And then as the sun gets lower, the temperature inside and outside the dome converge rather quickly. And at that point, we managed to converge almost to 0. And this is I believe, in summer or late summer of this year. A lot of these lines, each one of those lines is one individual night, and then try to highlight what the median is and the kind of the RMS spread around that. So this is during the day. And on the right, shows actually how spot on we were at the start of observations throughout a year of commissioning and early operations. So this is how close we got to the inside and outside dome environment being even throughout the months. And you can see that orange on the right upper panel, that orange box there, that is when we got the first 6 louvers working. And so we were able to actually get very good venting in that evening critical time to be able to stabilize the dome and equilibrate the conditions inside the dome. And the distribution is quite a bit more peaky after the louvers were installed, and that's the lower right panels there shows the histograms. Part of also was our improved evening temperature forecasting of the outside temperature. So we're able to more accurately predict what the evening temperatures were over this last year. So using the commercial prediction forecasting on the right there is Medio Blue, and we found the spread was something like 2 degrees off typically from the actual nighttime temperature that we saw on the summit. And just doing a real regression using our weather tower data, we were able to create this new predictive algorithm and immediately get about half of that spread and error under control. And recently we also have a new algorithm that's even below 1 degree now in RMS 3 hours prior to 3 hours prior to sunset, which is about the last point of we're able to adjust things is about 3 hours, because we do have to control the mirror, and the mirror has a lag of about 2 hours. So you can't make too great of corrections at that point after about 2 or 3 hours before the evening. So this is at nighttime. So I can also show here that the louvers help not only in venting during the evening time, but also stabilize the dome at night. So before the dome before the 6 louvers were installed, we had dramatically poor donut blur in our observations. And once those 6 louvers came online, we immediately saw about half a second at least improvement in most wind conditions. And then with 12, it's a little bit more subtle, and at certain relative wind angles, we also see quite a bit of difference in improved donut blur. Going to M1, M3, reminding people we have these fan coil units that pull air outside out of the mirror, condition it, and then create a positive pressure that pushes air back into each one of the honeycomb cavities inside the mirror. And that is basically how we control the temperature inside the glass. Where we also are servoing that system using the EAS, and we command it to basically follow the nearby air temperature outside the cell and the mirror to make sure that there's no mirror seeing. And also, which we found is very critical, is to reduce the overall gradients inside the glass. Yeah, so this is basically how well we're controlling the bulk temperature, and also showing that we're not seeing too many instances of actual mirror seeing. So that's distortions and inducing instabilities in the air above the glass. Then the latest initiative is to actually tune up the speed of the fan coils, but the speed of the fans themselves, and that is to speed up the reaction time of the glass as we're tracking the outside of the inside temperature of the air that usually follows the outside temperatures of the outside environment. So we can better follow along in that initiative. But we can't do that too quickly, because that we do induce mirror gradients. So there's a balance act that we're having to take, and one of them is to tune each one of the air nozzles, which feeds the air from the inside of the cell into the bulk glass, and that is to make the airflow more homogeneous across the whole mirror, so that if we're pushing more air through, we don't induce these larger gradients as much. So that is an ongoing thing that's almost complete. We have I think a few dozen nozzles to insert, and those are of course the hardest ones to accomplish. So that'll happen in the next few months, and we'll complete that. One more minute. Okay. As we're improving those radial gradients, we also improve the Z gradients, which is the front to back glass temperatures, which are more important for the AOS system to perform as well. Oh, there's a lot of slides. So this is basically the latest results that we have from improving the Z gradients and being able to servo the glass more quickly as we ramp up in fan speed. And so this is the latest results we have from the mirror control of the thermal systems. Okay, and I'll just leave the summary there.
So next we have a presentation by Craig Lage from UC Davis on the pointing model update. Pointing model, not updates on the pointing model. And in the meantime, if there's any quick question on the thermal performance. Yes.
How does the image quality improve or deteriorate from the beginning to the end of the night?
Can you repeat real fast? Can you repeat that?
How does the image quality is there a systematic change in the image quality from the beginning of the night to the end of the night?
It depends on if the temperature is rapidly changing. If it's stable, it's stable, right? The image quality doesn't vary very much if the atmosphere is stable and the inside dome environment is stable.
And if you include all of the nights, how does the image quality change from the beginning of the night to the end of the night?
I mean, it just tracks. The worst that we've seen is probably 0.7 arc second full with half max to up over 2 arc seconds full with half max intranight.
Thank you.
Okay, hi, I'm Craig Lage. I work at UC Davis and partially supported by the Rubin Observatory. I'm going to try to tell you our status of the pointing model. I'm going to give you a summary of the pointing model learning in the past year. And okay, yeah, that's better. Okay, and I'm pretty much just reporting these. I don't make a lot of these changes, but I've been reporting the results. And then at the end, I'll show you some of the impact of the pointing model errors on the image quality. For people that aren't familiar, what the pointing model means is that we want to point the telescope at a certain RA deck, but it's an alt-az telescope. So we point it in alt and as. So we need a model to tell us to get to this RA deck, I have to point at that alt-as. And so let me just, like I said, I'll give you some update on what we've done in the past year. This shows about a year ago. And so what this is we pointed the telescope at a certain RA deck, we think. We take the image, then we get an astrometric solution for the image and find out we actually pointed at that RA deck. And this is just a histogram of the distance on sky in arc seconds between where we thought we pointed and where we actually pointed. So we were around 30, 40 arc seconds about a year ago. And then we made a change to the lookup table, the open loop that, and it made things worse. So we went up to around 100 arc seconds. So then we corrected that, and it got much better. You probably can't read the numbers, but the median got to 15 arc seconds. But on the right, you can see there was a dependence on the rotator angle. I think this was driven by the fact that the center of rotation of the rotator is not exactly in the center of the image plane. So that's what caused that V-shaped dependence on rotator angle. And so then that got corrected, and now we're down to 6 arc seconds in the upper left. The median is about 6.5 arc seconds, and in the bottom, the dependence on azimuth, elevation, and rotator angles pretty flat. So we ran this way for a while, looking pretty good. We were pretty happy with that. Then we made a change to what are called the V modes, which caused larger motions in the camera hexapod. They got much worse. You probably can't read it, but it's a median of 68 arc seconds. And so we had to take that out. When we do these AOS corrections, moving the hexapods or tilting the camera, tilting M2, all of those things move the image. And so we had to compensate for that. And so a lot of work by Tiago Ribeiro to put that into the pointing model so that we compensate for that. And so this is where we are, or we were before we shut down, median about 7 arc seconds. And if you see here, there's this strong sinusoidal dependence on azimuth. So that's the next step. We think that's because the rotation axis of the azimuth axis is not quite vertical. I mean, we know it's not quite vertical, but the parameters that tell us how far it's off east-west and north-south need some adjustment. And you couldn't really see that before because of this other dependence on the AOS parameters. Now that we're compensating for that, we can see that very clearly. Hopefully we get that done before we're back on sky. So then what about impact on the image quality? So we have a lot of data on from the guider chips we have 8 CCDs in the corners, which are read out roughly every 100 milliseconds. So we get during the 30-second exposure, we get multiple images from those guider chips. And on the left here, we actually get a movie, but I just have one still from the movie. So in the movie, you can see them dancing around due to the atmosphere and mainly due to the atmosphere. But in addition to them dancing around, there can be a shift. Like on the right side, you can see that line where it's shifting. And the main reason it's shifting is because the pointing model isn't quite right. And if I plot here, the blue is given the measured pointing drift. I'm sorry, given the measured pointing error, we can calculate how much should the image drift, because we're not guiding. We have these guider chips that we're measuring, but we're not guiding the telescope. We're just blindly following the sky. And so if we're pointed here, if we think we're pointed here, but we actually pointed here, the guiding is the guiding is a little bit off, or the tracking is a little bit off. And so the blue is a predicted error that you would get given the known pointing error, and the orange is the measured from those guider chips. And you can see they track pretty well. And at this time, the pointing model error was on the order of 100 arc seconds. And your first thought would be, oh, this is really bad. We're off 0.4, maybe up to 0.6 arc seconds. But the impact on the image quality is not as large as you'd think. Basically, the drift over the 30 seconds divided by the square root of 12 gets added in quadrature to the image quality. So it has an impact, but it's not huge. And then this is a similar thing when we were down at around 10 arc seconds. And you can see they're still correlated, but the shifts are smaller. And I think if I can go back here, when we get this corrected, we should be down on the order of 1 arc second. So hopefully that's where we'll be here fairly soon. Okay, that's what I had.
Thank you, Craig. Do we have any questions while the next speaker sets up? Which
one over here.
So 1 arc second sounds great. As one thinks about the PSF error budget, does one have a sense of how much that will improve our image quality overall? I'm not sure that's a well-defined question, but
well, like I said, it should be if you have yeah, it's very small. That's 1 arc second of shift on the sky. So that's a much smaller drift. It'd be, less than a tenth of arc second, which then gets divided by the square root of 12 and added in quadrature. So if we have 1 arc second pointing error, it should be negligible.
I see. Keith, do you want to add anything to that? Or
Yeah, I mean, because it was at about a tenth of an arc second contribution back when we had these issues that Craig was describing. So exactly as Craig described, it'll basically become totally in spec negligible once we have all these improvements in place.
All right, great. Thanks. Next, we'll have from a student here at Stanford, working on the guider.
Yeah, hello. I am Jackie Zhang, and I'm gonna talk about my work on monitoring atmospheric scene using LSST guide stars. So I'll give an overview of how this method works, and then show some recent results. So here's a quick review of the atmospheric scene. So the light coming from a very distant source is effectively a plane wave before it enters the Earth's atmosphere. However, as it travels through the turbulent air in both the atmosphere and the dome, the wavefronts will get perturbed. So as a result, the incident angle for each photon is slightly perturbed by the gradient of the wavefront. So this has 2 effects. The first one is that it smears the images, and this is famously known as the atmospheric PSF. And the other effect is that if you take continuous and fast exposures of a star, for example, here, so this is taken from the guider sensor, then you'll be able to see that the star will jumping around between consecutive frames. So this is known as the centroid motion. So it turns out that if we know the shape of the turbulence power spectrum, then we can infer the atmospheric PSF size from this centroid motion. Okay, so what we do is for characterizing the centroid motion, we just simply take the variance of a star's centroid across all the frames in a given duration of a guider movie. So now, if we know the power spectrum of the turbulence, which fortunately we do thanks to Kolmogorov and von Karman, then we can come up with a quantitative relationship to turn the variance measurements into this R0 parameter, which is a amplitude parameter for the overall turbulence strength. So from there, we just convert this R0 to full width half max using this rather well-known relationship. Okay, so this is how using individual stars we can say about atmospheric seeing. But in reality, we have for LSST cam we have these 8 Guider stars located at the 4 corners of the focal plane. So it turns out that if we look at the correlation between these Guider star motions, there's also information about atmospheric seeing. So just to consider for a pair of stars, so if there is a turbulent layer, say at the high altitude, then it is likely to introduce uncorrelated motion for these 2 Guider stars because the light paths of the 2 stars are very far apart at high altitude. However, if we take this, if the turbulence layer is at lower and lower altitude, then the stars' light paths begin to overlap. So that is more. So the centroid motion between these 2 stars will be more and more correlated. So this work gave us the idea that we can look at the common mode of centric motion, differential centric motion, or uncorrelated centric motion to tell roughly where is the turbulence whether it's from the low altitude or high altitude. So more precisely, if we have a height-dependent turbulent a height-dependent profile of turbulence strength like this Cn squared shown on the top plot on the right, then by looking at the covariance and the differential variance of the 2 star centroids, we can come up with an estimate of the integrated turbulence strength with respect to the red and blue curves respectively. So that gives us roughly an estimate of how much atmospheric seeing coming from due to the ground low altitude portion or the high altitude portion. So with all the pairs of these 8 Guider stars in the LSST cam, then we can actually do something more. So we can do sort of a 3 layer separation of the atmospheric turbulence strength rather than 2. So the green one that is very sensitive to the high altitude is roughly we call the free atmosphere piece, and then for the lower altitude piece, we can actually separate a very sharp blue curve, which is predominantly a ground layer and to some extent also the dome seeing. And then in between is the orange curve, which we call the middle layer. So in summary, just from the centroid motion of those 8 Guider stars, we can get an estimate of the total atmospheric seeing and plus the 3 numbers which are integrated turbulence strength with respect to these 3 curves. Okay, so here is an example of what we get for one night. So the black curve is the total seeing estimate. So yeah, just from the top panel, the black curve is the total seeing, the total estimated seeing from the image motion of Guider stars. And we compare to the red curve, which is the measured atmospheric full width half max from the science images. So that is taking the PSF size of the science images and minus the AOS active optics contribution in quadrature. So in theory, they should agree, but in practice, you can see that for most of the times that they agree in amplitude, but sometimes they do not. But when that happens, still the change with respect to time for the black and red curve tends to agree well. So that's some sort of validation of how well this method works. So again, on the top panel, the blue, orange, and green curves are the layer separations as introduced before. And for this, they're converted to the full width half max in arc second. For the bottom panel, it's another plot that shows the relative contribution for each of the layer to the total atmospheric strength. So that's normalized to 1. Okay, and here is some summary from for the past 2 months. So on the left, it is So on the left, it is the comparison of the Dieter estimated full width half max with respect to the estimated image quality from the science sensors. So overall, you can see that they agree well. They track around this one-to-one relationship, and the correlation is good. So on the right, it is comparison with this RINGS. RINGS is a dedicated seeing monitor at Gemini South, and it also gives a free atmosphere component. So we're pretty close to each other. So we expect that the free atmosphere piece is probably similar. So in reality, we can also see that they tend to correlate well. And finally, for the next steps, we are most interested in the ground layer seeing. So we hope to make some correlation analysis, look at the ground layer seeing, and diagnose what sort of dome environment would impact the ground layer or dome seeing. I think that's.
While the next speaker sets up, do we have any questions for Jackie? All right, I don't see any questions. If the next speaker, Tom, would mind joining us on stage, or is it remote?
Hello, I can't tell if I'm an ethereal voice or a floating head, but I'm here. Do you hear me? That's the first question.
Oh, yeah. Sorry. Did someone ask a question right now? Or I didn't quite. Oh, that was Tom. Okay, yeah, go for it.
That's me. I'm clearly an ethereal voice.
Yeah. Sorry. Oh, there you go. We see you now here on the screen.
Okay. How do you want to do it? Should I share screen or should somebody stand near the laptop and I yell next? Which way do you want to do this?
I think it'd be easier if you share a screen, probably.
Okay, great.
Do you mind if? Is that his screen? Oh.
Being shared.
Hold on 1 second.
Did it do the thing? I think I see it.
All right, try now. Change slide. Okay, yeah. I think that worked. All yours. Thanks.
Great. Okay. Thanks, everyone. Apologies, I can't be there this year, but I wanted to talk to you a little bit about the work that we've been doing as an in-kind contribution to what was formerly known as SITCOM, verifying the LSST astrometry using the data previews. But we get our astrometry from, starting at the very beginning, the images that the telescope takes as they pass through the data reduction pipeline. And in this toy model on the right here, you see if I slide my PSF model left and right through a one-dimensional cutout of my image, my least squares minimizer in this case would at some point pick a best position for my source, which would be reported in my photometric catalog. But we also get this second order information from the width of the parabola of the chi-squared distribution, which we then report as the confidence we have in that detection as a covariance matrix. And these are used in things like the pipeline itself later on to determine things like proper motion and parallax for stars, but then they're used further downstream as well to solve things like the counterpart association problem of probabilistic cross-matching. But what we want to know is whether the positions and precisions that are reported in our photometric catalog are correct, by which I mean, do they agree? And if this was an experimental lab, I could shine my laser at my crystal many times, and I could report the scatter of my measurement of whatever I was measuring from my crystal. as my experimental distribution of my noise profile, and I could compare that with my formal uncertainties. But certainly in the case of the coads, we only ever detect each star in the sky once. So we have to do other things such as create ensembles of what we're going to call the same star for some given definition of same. And then if we can calculate their deviation from true on the sky, get their experimental errors, we can gain our scatter that way, which we can compare with these formal uncertainties. And if we do this for a set of magnitudes, signal-to-noise ratios, or covariances, which we hope tell us the same information, and in fact, that's sort of what we're trying to verify here, then we can compare this experimental error against our formal uncertainties, which we can parameterize. And then once we've got those parameterizations, we can zoom out, look at different bits of the sky, and analyze those parameterizations as a function of something like right ascension and declination. But I said deviation from true a minute ago, but that's not very useful because, of course, if we knew the real positions of all of the sources on the sky, our jobs would be a lot easier. So we have to turn to higher astrometric precision data sets, which in today's day and age means Gaia, really. But Gaia is frustratingly bright for LSST, so we supplement this with the Hubble source catalog to go below the Gaia completeness limit, giving us in what follows this 2x2 matrix of investigations that will be performed using two different truth tables to compare to the COAD object table and the visit-based source table, which introduces again this idea of repeat observations, because now we do actually have multiple observations of the same bit of the sky. And this looks like something like this for data preview 1, going actually from right to left here. Apologies for the way I put the slides together. Where on the right here, you start off with, as the black solid lines, the formal uncertainties from the pipeline of some set of these same objects. And then we have their deviations from true as distributions in the error bars, which are then fit for, which become single data points in this intermediate plot. And each of these pointings then are parameterized, as I said, and become individual data points on the left-hand side, which we can then look at as a function of sky position. But nobody cares about data preview 1 anymore. We have data preview 2. So here I'm showing analysis of the object table when we use the Gaia dataset as our truth table. And again, the analysis flows from right to left still. We compare covariances with scatter, which become data points, and single pointings become parameterized on the left. And the first thing to note is just that this n parameter, this bright systematic uncertainty that has to be added in quadrature in our model, is something like 5 to 10 milliarc seconds, seemingly decreasing with a density on the sky, while the m parameter, which is the scaling relation between scatter and covariance in faint photon noise dominated regimes, varies from about 2 up to 6 with increasing density on the sky. But don't think of that necessarily as density on the sky, because if I show you this plot from RCN 11 of the number of visits that went into the coads, you can see top left to this figure, there's some correlations there. So it's probably better to think of this as the m value increasing with the number of images that went into the coad. But the point to highlight is that this number is large. It is larger than 1, which we would like it to be. And you see something similar with the source table, the visit-based catalog, as compared with Gaia again, where once again we see this 5 to 10 milliarc second systematic uncertainty that we have to add in quadrature, now actually seemingly to decreasing with density ever so slightly, where this is a real density, of course, because the source table is based on single visit exposures, so there's no correlation with the number of images that went into the coat here, because they're all the same completeness limit thereabouts. And now our m value is fixed, is flatter at around 2 plus minus a bit. And again, the point to highlight here is that this m value should be 1 and is slightly higher than that. And if I now switch to the Hubble source catalog as my truth table, the first thing to note, of course, is that you get many fewer data points because Hubble is not an all-sky data set like Gaia is. But actually, the second thing to note is on the left-hand side here, m is 1. With not very many data points. But you can see this on the right-hand side. There's a few examples there where we now see that the covariance and the scatter agree, something like 27th magnitude in this example. And we report a 50 milliarc second systematic uncertainty. And the source table, as compared with the Hubble source catalog, shows something similar again, where now we have more data points on the left-hand side there because we have this repeat observation. So we have higher number statistics with the source LSST table, where with this better, we have slightly higher confidence drawing a line through m equals 1. And again, I show an example of scatter and covariance agreeing on the right-hand side. And we report again this n of about 50 milliarc seconds. But just to allay your fears there, if I show you the Gaia analysis of a single point of the sky and the same Hubble observation on this figure, essentially what you can think of that Hubble n value as being is an upper limit, where the hyperparameter fits just don't have any information below their brightest, highest signal to noise ratio data points, so they cap out basically. So think of, at least in the Hubble case, that's systematic as an upper limit. And I will leave you with my conclusions there and leave you with some open questions. Thank you.
Tom. Thank you very much. Do we have any questions for Tom while the next speaker sets up?
So just checking these, I think I've lost track of what we actually did in DP2. So the Gaussian process overlay, improving the WCS, that is present in this analysis?
I believe that's
Or
what
not?
Claire said yesterday. That's why I added this provocative, is it turbulence? Because this number matches the numbers that was reported in Claire's talk yesterday in the SMWLV session, which may be a coincidence, but it seems tantalizing to me. But the problem I have is I'm doing natural philosophy here. I can't actually explain these results as I'm doing the proper end-to-end test. And there's Claire now.
Yeah, I just wanted to
Wow.
confirm, if you didn't see my thumbs up, that yes, the DP2 results do include the Gaussian process overlay.
So this might be a coincidence, but that seemed interesting to me, that the number that is subtracted out by the turbulence model agrees with that number that I am finding, but that could be a coincidence.
Okay. All right. Thanks.
Thank you. Hold on a second.
You'll have to say when to release the screen share. I can't see anybody.
Would you mind stop sharing, Tom, please?
Yeah, okay. Thanks, everyone.
Thank you. Thank you. Great. Thanks.
Hi, my name is Anya Wyant. I'm a postdoc with Michael Wood-Vasey, and I'm excited to share with you today what I've learned about measuring water vapor with GPS. Precipitable water vapor is particularly important in the Z and Y filters. Water vapor is measured in millimeters of liquid, as if all of the water vapor in a column were condensed along a line of sight. Here I'm plotting LSST throughput curves. You can see the filters on the bottom. I've plotted a fiducial atmosphere at an air mass of 1.2 as the gray dashed line, and the precipitable water vapor contribution are the blue lines at the top. And you can see that it's the dominant component of the atmosphere between the Z and Y filters. And this is important for observations of objects like type 1a supernova who have a complicated SED that may interact with these bands in a redshift dependent way. So water vapor delay is part of the GPS navigation solution. So the main observable in GPS positioning is the travel time of a signal to travel from a satellite to a receiver on the surface of Earth. So we take this travel time, multiply it by the speed of light, and we calculate a range. And if we know the location of all the satellites in space and we know all the ranges, we can isolate our position on the surface of Earth. But before we can do that, we have to correct the range for a whole host of errors. So we have to consider special and general relativity, the ionosphere, the troposphere, instrument delays, receiver delays, even Earth deformation effects due to the tide. We actually understand how to do this very well. And so the effect of the troposphere on the signal is a delay in the arrival time. So it's customary in high accuracy positioning to project this delay to the zenith direction and actually add it to the navigation equations as a term we solve for. So in addition to position, we measure the variable wet delay in the zenith direction. Once we have this delay, we can combine it with pressure and temperature information, and we can convert to precipitable water vapor with only 2 to 4% additional uncertainty. So we installed a Trimble Net R9 receiver and a Zephyr 2 antenna at Rubin. You can see the antenna is mounted on the DIM tower, and the receiver is housed in an electrical box at the base of the tower. And we have continuous measurements of the water vapor from that date, except when we have power outages or weather data gaps. And so on the bottom, I'm plotting here our estimates for the water vapor for the first 6 months. So we have kind of spring heading into summer. And you can see that the water vapor is getting more variable in summertime. And it may look like noise to you, but these spikes are actually just the daily variation in the water vapor, which we expect just from solar heating of the Earth's surface. So we've been measuring water vapor precisely and accurately. The details of why we think we're precise and accurate are in this paper that's currently under review. But we think our accuracy is 0.9 millimeters, our precision is 0.4 millimeters, and our temporal resolution is 15 seconds. But I actually think we can do better than measuring just water vapor in the zenith direction. So we can model the first order asymmetry of the troposphere by imagining that our troposphere is a slab, and we tilt the slab such that we have more time delay in one direction and less time delay in the other. And then we can define a vector that's pointing in the direction of maximum time delay. And then we break that vector up into its north and east gradients components. And we add these to our navigation equations. So now in addition to position and wet delay, we're also measuring our north and east gradients. And so here on the right, I'm plotting the average gradient for the month of September and the month of December as a function of time of day. And the first thing I'd like to point out is that the north gradient, which is plotted in blue, is positive. And this is actually expected much more water vapor in tropical regions than in polar regions. So we expect our north gradient, north-south gradient to be pointed north. It's also known that gradients point towards higher altitude. And so since Rubin Observatory is next to the Andes Mountains, we also expect our east gradient to be positive, which we see. So what do these actually look like on the sky? So here I am plotting the precipitable water vapor in millimeters of just the gradient component. I have for 2 nights in September. So we have September 6th and September 13th. The gradient component, of course, varies with times, but in these plots, I'm just averaging over the night. And I've also included the telescope pointings for LSST and the auxiliary telescope. I have contour lines kind of marking the 0.25, 0.5, and 0.75 millimeters. And so you can see that the effect becomes more important as we are at lower elevations. But in the months that I've processed, we typically see these gradient components pointing to the north and northeast directions. So this could potentially be a source of systematic error, especially for these lower elevation observations. And so finally, it is possible to measure additional delay beyond the isotropic component and our first order asymmetry. And we do this with post-fit residuals. So the post-fit residual is just the measurement of our range to the satellite minus the model. And so this residual includes systematic error and noise, but it also includes local variations in water vapor. And so on the left, I'm plotting different satellite tracks over 3 hours for a night in December. And perpendicular to these tracks are the post-fit residuals. So red in this case would indicate more water vapor, and blue would be less. And in the kind of the northeast corner, I have a little black mark that indicates the size of 1 millimeter of precipitable water vapor. So this is sort of ongoing right now, but the question is how much of this signal is correlated noise and what is actually water vapor? And so sort of this is still very investigative stage. On the right, we downloaded data from the ERA-5 global atmosphere reanalysis data set, and one of their variables is total column water vapor. So we subtracted out the daily average to kind of remove some elevation dependence. And we're trying to see if the variation in the ERA-5 total column water vapor is reflected in our post-fit residuals. So our key takeaways are just that we feel that we can reliably retrieve precipitable water vapor with our receiver. We've been doing this at Rubin, and we think there's potential to measure additional water vapor along lines of sight. Thank you.
Thank you very much. We have time for some questions.
Sorry, I think I missed something super basics. Okay. I think I missed something super basic. So, when you measure the times, there's all sorts of delays,
Yes.
as you said. So how are you isolating the water vapor signal?
So the water vapor signal for each so we the time delay for each satellite is multiplied by a mapping function, and we project it onto the zenith direction. And so when we converge on our position of our receiver, we find X, Y, and Z position, a difference in clocks, and the variable wet delay. Right.
How do you know that it's not due to something happening in the troposphere or some other effect? That's the part I'm missing, the basic effect.
Okay,
there's
so
all sorts of things that can happen, right? So.
Yes, so we incorporate models for most other effects. The dominant signal from the troposphere is the water vapor. So we have models for the dry gases in the atmosphere that work very well. This is where the pressure and temperature measurements come in. The model is we measure the additional delay that the signal must have undergone in order to isolate our position. I don't know. Sorry. Oh no, totally. It took me a while as well.
Thank you. I see a question from Eli, but before we have a question online, if you don't mind, we'll address that first. Could someone read it out loud for us, or if not, I will do it myself.
Or just Douglas, can you ask?
Yes, sorry. I was sorry I was gone through the normal channels of putting it in the chat, but this is very interesting. For Dark Energy Survey, we also had a a precipitable water vapor monitor through GPS. I was wondering, do you would it be of at all interest as a baseline or to as a cross comparison to use data from the GPS monitor on Tololo, which also measured precipitable water vapor and combine results, or combine and or cross compare results?
Well, it would probably would be interesting in terms of looking at the gradients, because I think these are kind of related to water vapor transport throughout the day. So I think it would be interesting to have measurements from a nearby location.
Mhm.
So yeah, I think that would be interesting.
Well, thanks.
Been run the GPS water vapor on CTIO.
Yeah.
Okay.
CTIO.
I didn't realize it was resurrected. We didn't have it for the last few years of DS.
Oh, I don't know
anyway.
if it's I doubt it's for I doubt I mean I think the equipment is there. I'm not
Oh,
sure.
yeah. Oh, yeah. Okay. If no one is operating it, then it hasn't been running in 8 years.
Yeah.
7 years. I don't know. 4 times.
Mm.
So I actually did not understand the gradients and what that was a gradient of in terms of
Okay.
because
I can,
you know for the I guess in yeah.
Oh, sorry.
That
And so they call this the tilted atmosphere in the GPS literature. So we imagine tilting our slab of an atmosphere. And I think you can picture it as like, for instance, the nearby mountain range pushing the atmosphere up. And we find the signal in the GPS time delay as an increased delay in one part of the sky and decrease in the other. So in the picture on the left, the atmosphere is tilted from a neutral position. So the yellow component of the time delay should be the isotropic. And then this I think pink area would be like the additional delay due to the atmospheric tilt. And
don't I what I care about is the impact on the photometry, right? And I'm not I guess I'm not picturing which cares about the water vapor, looking out between our observatory and
right.
the atmosphere.
So there is work being done on what the physical interpretation of the gradients are, which is why I brought up that the gradients are always pointing towards higher elevations. It is known that adding these terms helps you converge more accurately in your positioning solution. And these terms are typically used in weather forecasting. I don't know what they mean precisely at Rubin. We just started measuring the gradients last month.
I don't know if you were there last night when I learned from Ian, who I don't know if he's here, that the water vapor impacts the DCR in the U and G, and that was news to me. Maybe everyone knew this or no one knew this. I don't know, but we have no impact photometrically when we're observing in the blue bands of water vapor, but apparently it does impact the differential chromatic refraction. So this is going to be the only way I know right now for us to get that, because I guess Oxtel as well is, but we'll want to. Anyway, we'll talk.
Yeah, so
later.
sort of the next step was to look for the gradient signature in the Oxtel data to see if this is a significant signal, but that's ongoing.
Thank you very much for this interesting discussion. We had planned some time for Q&A, which I think we stand by still, the people from the team. So if you are willing, you want to go for lunch, feel free to do so. If you want to ask some questions, we have some backup slides and we're happy to answer those questions as they come by. So see one over here.
And I don't remember what full system there's either pin. In the full system, there's either a pin cushion or barrel distortion. How much is it? Have you corrected for it? There's it's a classical sidewall aberration. It's either pin cushion or barrel distortion. If you call it,
Yeah,
so like,
you don't measure the classical sidewall operations, but are you asking typical about that?
well, you have to correct the
Oh.
you have to correct the full field of view for
Yeah.
distortion. You do that.
Oh, yeah, we do that. Yeah.
Okay, right, fine.
I see there's an exodus of people. All right. Well, if no one has any additional questions. Oh. Yeah, I'll give it to you.
Yeah, I have a question about the breakup in different layers of the turbulent layers. I was curious to what extent those different layers, the amplitude is correlated in your solution. To what extent is the amplitude of the turbulence in the different layers correlated in the solution? Yes.
Yeah, so yeah, it will be correlated because ideally we want a top hat separation, but so the correlation is then just given by how much those kernels overlap. Does that answer your question?
It's curiosity, yeah. Any case,
Yeah.
it's
So
really
there
cool.
will
It's
be
really cool
correlation.
analysis in any case.
It's not a very clean separation.
Thank you. I think Anya had another question.
I was actually wondering if anyone in the room could help me, but a large source of error that we have with the GPS water vapor is reflection off of nearby surfaces of the signal. And since I'm the receiver or the antenna is located right next to the DIM dome, I'm getting interference from when the dome is closed and when it's open. So I was wondering if anyone could help me find out what those times are. Okay.
So any time after 12-degree twilight, it's open if the telescopes are open and the system is enabled, CSC speak. There's supposed to be telemetry to show you that the dome is open and closed. I don't think that's populated yet.
Thank you. I guess to address one of the questions earlier from Paul, in which you were asking, do you expect throughout, the hours of the night to see, well, what do you see, whether the image quality gets better or not? And I can tell you that, right. Right. Yeah. So I just wanted to bring it up because I was quickly checking, and you can indeed see that, it gets better towards the end of the night. Well, no, it gets better as the night progresses, but towards the end of the night, it gets worse again. Golf. Yeah. It's pretty flat, so it doesn't change that much, but I can show you later if you want to. Yeah. Oh, correctly.
Yeah, I had a question for Anya. I think we're routinely getting the precipitatable water vapor from Oxtel. So have you tried correlating?
I have. So when we compare with Oxtel, we have an RMS of about 0.7 millimeters. We have to sort out some normalization issues on our side, and I wasn't sure if Oxtel also had similar normalization issues. And I have been using the data to look at some of the gradient changes, but I haven't confirmed any of those results yet.
Thank you. Now, I think we'll close the discussion. Sandrine has a quick announcement to make, and after that, I hope you all go get some lunch.
Yes, so I really think there's very little people left, but mostly image quality. So we're actually working with the SPIE referee side of the journal, which is called JADIS, on a special edition, really focusing on the ribbon image quality. So the link, I will make sure that it is available for everyone. The idea is for the people who posted SPIE papers, we can actually use those and tweak them slightly, but submit those as they are. And then for other people, if you have new ideas and new paper you want to submit to that special section, you can before October 31st. So I just wanted to make sure that people knew about that. That's all.
Thank you very much. And thank you all for staying some overtime. Yeah, thank you.